Our moon, a familiar sight in the night sky, has long captivated humanity. Its gentle glow, its rhythmic phases, and its influence on tides have inspired countless myths and legends. But the moon's origin story remains shrouded in mystery for centuries. Scientists and philosophers alike pondered how this celestial companion came to be. Was it captured by Earth's gravity? Did it form alongside our planet from the same primordial cloud of gas and dust? Or was a more dramatic event responsible for its birth? For decades, the prevailing theory among scientists was the giant impact hypothesis. This theory proposes that the moon was formed from the debris ejected into space after a cataclysmic collision between the early Earth and a Mars-sized object. This event, thought to have occurred over 4.5 billion years ago, would have reshaped our planet and given rise to the moon we know today. Recent scientific discoveries have provided compelling evidence to support this theory. By analyzing lunar samples brought back to Earth by the Apollo missions, researchers have uncovered striking similarities between the composition of the moon and Earth's mantle. These findings, along with sophisticated computer simulations, have solidified the giant impact hypothesis as the leading explanation for the moon's existence. The story of the moon's formation is a testament to the power of scientific inquiry. In the early solar system, chaos reigned. Planetary bodies, large and small, collided with each other in a cosmic dance of creation and destruction. It was during this tumultuous period billions of years ago that a Mars-sized object called Theia is believed to have collided with the young Earth. This impact, unlike anything humanity has ever witnessed, released an unimaginable amount of energy. The energy released by this impact was so great that it melted the outer layers of both Earth and Theia, creating a vast swirling disk of molten rock and vaporized material. This disk, bound by gravity, gradually cooled and coalesced over millions of years, eventually forming the moon. The giant impact hypothesis explains several key features of the Earth-Moon system that had puzzled scientists for centuries. For example, the moon is relatively large compared to Earth, and its orbital plane is tilted with respect to Earth's equator. These characteristics are difficult to explain if the moon formed independently or was captured by Earth's gravity. However, the giant impact hypothesis elegantly accounts for these observations. The impact would have blasted a significant amount of material from Earth's outer layers into orbit, providing the raw material for a large moon. The off-center nature of the collision would have imparted angular momentum to the system, explaining the moon's tilted orbital plane. While the giant impact hypothesis provided a compelling narrative for the moon's formation, scientists needed concrete evidence to support it. One of the most convincing pieces of evidence comes from the analysis of lunar rocks. Specifically, scientists have focused on the isotopic composition of these rocks, comparing them to rocks found on Earth. Isotopes are atoms of the same element that have the same number of protons, but different numbers of neutrons. For example, oxygen comes in 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The relative abundance of these isotopes can vary slightly depending on the geological processes that formed a particular rock or planet. When scientists analyzed the oxygen isotopes in lunar rocks, they found something astonishing. The isotopic ratios were nearly identical to those found in Earth's mantle. This discovery provided strong evidence that the moon and Earth share a common origin. If the moon had formed independently, or been captured by Earth's gravity, its isotopic composition would likely be different from Earth's. However, the near-identical isotopic ratios suggest that the moon was formed from material that originated from Earth, consistent with the giant impact hypothesis. This discovery was a major breakthrough in our understanding of the moon's formation, providing tangible evidence to support a theory that had previously been based on circumstantial evidence and computer simulations. The importance of oxygen isotopes in unraveling the mysteries of the moon's origin cannot be overstated. These tiny variations in the atomic structure of oxygen provided scientists with a powerful tool to trace the origin of planetary materials. Imagine a cosmic fingerprint. Just as every human has a unique fingerprint, every planet and moon has a unique isotopic signature. By comparing these signatures, scientists can determine whether 2 celestial bodies formed together or independently. In the case of the moon, the oxygen isotope ratios served as a smoking gun, pointing definitively to a shared origin with Earth. The near-identical ratios found in lunar and terrestrial rocks suggested that the material that makes up the moon was once part of Earth. This discovery provided compelling evidence to support the giant impact hypothesis and revolutionized our understanding of the early solar system. The analysis of oxygen isotopes is just one example of the many scientific techniques used to study the moon and its history. By combining data from multiple sources including lunar samples, remote sensing observations, and computer simulations, scientists are gradually piecing together the story of how our celestial companion came to be. While the giant impact hypothesis had gained widespread acceptance among scientists, questions remained about the details of the impact and its aftermath. For example, what was the precise angle and speed of the impact? What happened to the remnants of Theia after the collision? To answer these questions, scientists turned to sophisticated computer simulations, recreating the conditions of the early solar system and modeling the impact in extraordinary detail. In a surprising twist, a recent astronomical observation provided an unexpected opportunity to refine these simulations. In late 2024, astronomers discovered a near-Earth asteroid, designated 2024 YR4, on a trajectory that brought it relatively close to Earth. While initial calculations suggested a small chance of impact with Earth, further observations ruled out any significant risk. However, scientists realized that 2024 YR4 presented a unique opportunity to study the dynamics of celestial impacts. By carefully tracking the asteroid's trajectory and analyzing its composition, scientists could gather valuable data to improve their simulations of the giant impact that formed the moon. Computer simulations have become an indispensable tool for planetary scientists, allowing them to recreate events that occurred billions of years ago. By inputting the known laws of physics and the estimated conditions of the early solar system, scientists can model the movements of planets, asteroids, and other celestial bodies. These simulations can be run multiple times, each time with slightly different starting conditions, to explore a range of possible scenarios. In the case of the giant impact hypothesis, simulations have been used to model the collision between Earth and Theia in exquisite detail. By adjusting parameters such as the size, speed, and angle of impact, scientists can study how these variables affect the outcome of the collision. These simulations have shown that a glancing blow, rather than a head-on collision, is more likely to produce a moon-forming disk of debris. The discovery of asteroid 2024 YR4 provided scientists with an unexpected opportunity to refine these simulations. By studying the asteroid's composition and trajectory, scientists could gather valuable data to improve the accuracy of their models. For example, the asteroid's elongated shape and rocky composition provided insights into the types of objects that were present in the early solar system. The study of the moon's origin is far from over. Each new discovery opens up new avenues of research leading to a deeper understanding of our celestial companion and its place in the cosmos. The giant impact hypothesis, once a controversial idea, has now become the leading explanation for the moon's formation. However, many questions remain unanswered. What was the precise composition of Theia? How did the impact affect Earth's early atmosphere and oceans? Did the impact play a role in the emergence of life on Earth? To answer these questions, scientists are planning future missions to the moon. These missions will collect new samples, deploy advanced instruments, and conduct experiments that will shed light on the moon's history and evolution. The moon is a treasure trove of scientific information, preserving a record of the early solar system that has long since vanished from Earth. By studying the moon, we are not only learning about our celestial companion but also about our own planet's history and the processes that led to the emergence of life. The search for knowledge is a never-ending journey. As we continue to explore the universe and unravel its mysteries, we are constantly reminded of the vastness of what we don't know. The discovery of asteroid 2024 YR4, while initially raising concerns about a potential impact, ultimately provided scientists with a valuable opportunity to refine their understanding of celestial mechanics. The data gathered from observing 2024 YR4 will undoubtedly lead to new insights into the formation of the moon and the early solar system. Science is a collaborative endeavor, driven by curiosity and a thirst for knowledge. The study of the moon's origin has brought together scientists from diverse fields including astronomy, geology, physics, and chemistry. By sharing their expertise and working together, these scientists have made remarkable progress in unraveling the mysteries of our celestial companion. As we look to the future, we can expect even more exciting discoveries as new technologies emerge and new missions are launched. The exploration of space is an ongoing adventure filled with wonder and discovery. As we continue to probe the cosmos, we can expect to uncover even more secrets about the universe we inhabit. To stay informed about the latest developments in space exploration, subscribe to our newsletter. We'll keep you updated on the most exciting discoveries, from new planets orbiting distant stars to the latest findings from missions to the moon and beyond. Join us on this journey of discovery as we explore the cosmos together.